Hello and welcome to Module GL302. You remember that in our previous module, GL301, Basic Drilling and Well Completion Technology, we discussed in some detail the equipment and procedures used in drilling and completing a well. Now it is time to install our production equipment and begin production. In this module, we shall learn how this is done. Our work divides itself naturally into two major areas: production technology and reservoir management. In production technology, the first half of the module, we shall be concerned with the physical principles behind the flow of fluid from the well and how this fluid, often a hot, high-pressure mixture of oil, gas, and water, is separated, cleaned, and measured for sale. In reservoir management, the second half of the module, we shall explore the natural energy sources which drive the producing reservoir and the methods used to improve the ultimate recovery of oil and gas.
A basic understanding of production technology and reservoir management is helpful to the explorationist and particularly to the development geologist for many reasons. For example, choosing well locations and revising geological interpretations in producing areas is often based in part on production performance data. Gaining an appreciation for the processing requirements of oil and gas production is important, particularly in the case of offshore areas, where economic and space constraints can limit geological objectives. Reservoir simulation requires close collaboration between the geologist and the engineer to define accurate reservoir models. We begin with production technology. Here we have two major concerns. First, the subsurface equipment needed to produce the fluids, and the surface equipment needed to separate, clean, meter, and sell them. And second, the performance of the well under natural flow or artificial lift conditions. Let's start with the subsurface equipment. We remember from module GL301 that as we drilled our well, we added several different strings of casing to support the hole, control pressures, and prevent fluid communicating between formations. The conductor pipe, surface pipe, and production casing strings were all cemented in place. The production casing string was then perforated over a selected formation interval. During the completion process, the first piece of equipment we add is tubing, sized to fit within the production casing string. The casing tubing annulus is usually isolated by a production packer, which is set just above the formation after the tubing is run in the hole. Having tubing in the well bore allows us to isolate the produced fluids from the casing and control production more easily. It also provides an opportunity for us to add downhole safety devices or artificial lift equipment. If problems develop, the tubing string may be easily removed. In high-producing rate wells, in the Middle East, for example, the tubing diameter may exceed 4 inches or 10 centimeters, while for lower rate wells, the tubing size will be in the 2 to 3 inch or 5 to 8 centimeter diameter range. The hole and casing size of the high-rate wells must be designed by the drilling engineer in anticipation of the need for larger tubing.
There are a number of components that may be added to the tubing string to meet various operating needs. Many of them are explained in your manual. Now let's go up to the top of the hole and discuss the wellhead, the piece of equipment that joins the subsurface equipment with the surface equipment. There is no single unique wellhead design, but in every case, the primary purpose is to safely control the flow of fluids under pressure.
The design of the entire arrangement depends on the expected operating pressures, the number and sizes of casing strings, the number and sizes of tubing strings, the need for auxiliary equipment such as subsurface safety valves and artificial lift equipment, the outside environment. Will the wellhead be located onshore, offshore, or at the sea floor? The inside environment. Will corrosive fluids be produced? The operator's safety policy and the prevailing safety regulations, the operator's equipment inventory, and preference for a given manufacturer. However, all these examples have several common components. The casing head is screwed or welded to the outermost casing stub. The inside of the casing head provides a sealing surface for the casing hanger, which grips the hanging casing and seals off the annulus between the outer and inner casing strings. Casing spools allow for additional casing strings to be hung and sealed off above the casing head, one spool for each string. The tubing head performs a function similar to the casing head, in that it accommodates a tubing hanger, which usually screws onto the top of the tubing string or strings and seals off the tubing casing annulus with metal-to-metal and/or rubber sealing elements. An adapter or bonnet provides a transition from the tubing head to the arrangement of valves and fittings located above the casing and tubing head, which are used to control flow. The equipment above the tubing head is referred to as the Christmas tree. The bottom valve, often called the master valve, is the primary means for completely shutting in the well. A T-type fitting allows for redirection of the vertical flow stream to a horizontal flow line. For a flowing well, the produced fluids, before entering the surface flow line, must pass through the smallest restriction in the surface flow equipment, the choke. The choke is used to control the production rate, perhaps to prevent sand production or to maintain the most efficient rate for the well. A choke restricts the area available for flow through a bean or orifice of a specified diameter that must be inserted into the choke body. The smaller the diameter of the bean, the lower the production rate. There are two kinds of chokes: positive chokes with interchangeable beans and adjustable chokes, which allow the choke size to be varied more easily. Note that tubing pressure is measured upstream, that is, on the wellhead side of the choke. We shall refer to this pressure measurement later in this module.
Generally, the size of both the tubing string and the surface choke have the greatest effect on the performance of a flowing well. Now let's continue with our description of the production equipment, in this case the surface equipment that exists further downstream in the production system. We all know that a well usually produces a mixture of oil, gas, water, and sediment at elevated temperatures and pressures. Sometimes we may produce little or no water or produce only gas, but generally all three fluids will be present to some degree. We may also have corrosive contaminants such as carbon dioxide, hydrogen sulfide, and dissolved salts produced in the oil, gas, and water. Surface production facilities are designed to turn this mixture into separate streams of clean oil and gas and safely disposable water. Only then can the oil and gas be metered and sold or sent for further processing to a plant or refinery. Let's follow the path of produced fluids from the wellhead through the various surface facilities to the point of sale.
The produced fluids leave the Christmas tree and enter a surface flow line system, usually a 2 or 3 inch pipe, which may be on the sea floor for subsea completions or below or above ground at onshore installations. If the production facilities are shared by a group of wells, as is often the case, the flow line will probably connect to a header or production manifold. The header is an assembly of valves which allows each well to be shut in or to be diverted to a particular portion of the production facilities, say for testing. From the header, the commingled stream of production from several wells moves on through the system. Normally, a separator is the first piece of production processing equipment that the produced fluid stream encounters. Its purpose is to separate the gas and liquid phases. Separators are usually classified by physical shape. For example, we might have a spherical one, or a single horizontal one, or a double-barrel horizontal one, or a vertical one. Each type is more appropriate for a specific application, and its size depends on the volume of produced fluids to be handled. A three-phase separator divides the production into gas, oil, and water. A two-phase separator divides the produced fluids into gas and liquid. Let's observe the operation of a typical vertical two-phase separator. The oil, gas, and water mixture enters through an inlet on the side of the tank-shaped vessel. The fluid stream immediately strikes a metal plate, which diverts the flow around the inner surface of the cylindrical separator, imparting a centrifugal motion. This motion throws the liquid to the outer edge of the cylinder and allows the gas to remain near its center. The lighter gas, now separated, rises through the center of the vessel while the liquid falls. Often the separator includes a system of baffles which spread the liquid out as it drops to the bottom of the vessel. This allows any gas bubbles carried in the liquid to easily escape. The gas phase, which is directed to the upper portion of the vessel, is usually passed through a mist extractor to remove minute liquid droplets entrained in the gas. This one, for example, is made of knitted wire mesh. There are other methods used to perform the same operation.
We engineers know that a higher volume of ultimate oil recovery can be achieved if gas is removed from contact with the liquid as separation occurs. This means that a long series of separators, each operating at a slightly lower pressure and allowing for the removal of the liberated gas from each stage, will allow for the highest oil recovery in the storage tank. This type of continuous separation is not economically feasible. However, multi-stage separation with 2 or 3 separators can approach the optimal yield, and that's what we often see in practice.
The oil separated at one stage goes on to the next. The gas is removed at each stage and is referred to as high pressure, medium pressure, or low pressure gas, depending on the stage at which it is removed. Field production facilities will usually have a high pressure gas system and a low pressure gas system. The low pressure system often being tapped for fuel or compressed to satisfy artificial lift needs. Let's now see what happens to the oil and water after it leaves the separation portion of our system. Later we shall see what happens to the gas. If the oil does not contain water or impurities, it may go directly from the separator to the stock tank or pipeline. However, in many oil fields, after initial separation, the oil must still be treated to remove water, salt, or contaminants. If the water and the produced oil settle out freely because of density differences, a free water knockout can be used to separate the two. A free water knockout is a simple separation vessel located along the flow stream, in some cases upstream of the separator, where the oil and water mixture is allowed sufficient time to separate. A more difficult separation problem arises when the oil and water are produced as an emulsion. We may break the emulsion and thereby separate the oil from the water by adding chemicals, by heating the emulsion, or by causing an electric charge to pass through the emulsion. Treating vessels utilizing more than one treating process to attack particularly stable or tight emulsions are common.
Another possible crude contaminant is salt. Even after separation and treatment, most produced oils still contain small amounts of emulsified water with dissolved salt. Salty crude may cause severe problems during refining. In such cases, the crude must be desalted. The procedure is relatively simple. The crude oil is first separated, and the remaining salty oil is mixed through a nozzle with fresh water. The mixing of the fresh and salty water in the oil forms a new emulsion, which can be separated from the oil, carrying the salt along with it. In areas such as the Middle East, where enormous volumes of oil are produced and prepared for transportation on a daily basis, a crude stabilizer may be part of the oil treatment process. Crude stabilizers, in these cases, separate the more volatile fluids remaining in the oil after normal separation. This ensures that the oil is suitable for storage and transportation, and that vapors from the storage tanks are not lost. Once we have installed equipment that gives us a good, clean oil, we have one remaining job to do: to meter it accurately for sale.
Crude oil metering can be either manual or automatic. Manual gauging of oil production involves the hand measurement of the oil level in a storage tank before and after oil is removed to the sales line. Automatic measurement devices can be subdivided into positive volume and positive displacement meters. Positive volume metering involves the filling of a predetermined volume, the automatic discharge of that volume by liquid level actuated valves, and the recording of the discharge by some type of counter. Positive displacement meters are highly efficient fluid motors used for measuring oil volumes. The fluid stream is divided into segments within the meter, and the movement of these segments through the meter is registered on a counter.
Now that we understand the options for handling crude oil at the surface, let's turn our attention to the gas stream as it leaves the separator or as it is produced from a natural gas well. In the case of produced gas, we are concerned with the removal of condensate, water, and corrosive or poisonous gases.
There are several types of gas treating vessels which remove condensate from the gas stream. A scrubber is a special type of separator designed to handle streams with high gas-to-liquid ratios. Often a scrubber is used in place of separators for wells that produce very light oils or condensates. The gas and condensates separate by gravity action within the scrubber. Another method of separating liquids from a gas stream is through low-temperature extraction. Essentially, the process causes the pressure of the gas stream to be reduced by having it flow through a choke, causing a sharp reduction in the temperature and the condensation of water and liquid hydrocarbons. Removing water vapor or dehydrating natural gas can be accomplished by a system that relies on the adsorption of water vapor on solid desiccants, such as alumina, silica gel, or calcium chloride, or by a system that relies on the absorption of water vapor in liquid desiccants, such as glycol or methanol. In the more common absorption process, a glycol solution enters at the top of the absorber column. Wet gas, that is, gas containing water vapor, enters the column from the bottom. As the glycol falls, it mixes intimately with the ascending wet gas, and the water vapor is absorbed in the glycol. Sweetening the gas refers to the removal of corrosive carbon dioxide and deadly hydrogen sulfide. This is usually accomplished by passing the gas through an amine solution or a column packed with iron oxide, called an iron sponge. The normal procedure for selling the gas is to deliver it to a pipeline. Because gas pipelines are usually operated at a relatively high pressure, the gas stream may need to be compressed to enable it to enter the sales pipeline. When the gas has been separated, sweetened, compressed, and if necessary, dehydrated, it must then be metered and sold. There are a number of methods available to measure gas volumes, but the orifice meter is the most widely used. The orifice meter relies upon the placement of a restriction in the gas flow line, normally an orifice plate, which causes a sharp pressure drop. By measuring this pressure drop as well as the temperature of the gas in the line, the gas flow rate may be estimated quite accurately. Let's now consider the processing and disposal of the produced water. Produced water, after passing through the separator and the treater, is normally disposed of by injection into disposal wells, by re-injection into the reservoir as part of a water flood project, or by pumping it into open pits and leaving it to drain, or by pumping it into the ocean. In every case, and especially in offshore locations, the removal of oil from the produced water must be extremely efficient and complete to eliminate any environmental hazards. For this reason, if a three-phase separator, free water knockout, or treater do not remove the oil from the water to an environmentally safe level, a coalescer or skim tank may be needed to segregate and recover the small volumes of oil still remaining in the water. The water is then usually metered before disposal.
Let's take a look at a typical West Texas production facility which incorporates many of the items which we've just discussed. This facility has been designed for a particular set of production conditions. Remember, other system designs will be different. To help you along, you might refer to the schematic that appears in your manual. We're here in Midland, Texas at a very colorful production facility, and here we'd like to show you how oil, gas, and water from producing wells are brought into this separation facility, show how the oil, gas, and water are separated, how the oil goes into the tanks behind me, how the gas goes into a gas line where it's compressed and sent on to sale, how the oil is picked up by trucks, and how the water ultimately is disposed of in the water collection tank. Let's begin first then with the producing wells. Let's see how the oil and gas are produced from the producing wells surrounding this production facility. Here we have one of the producing wells that produces oil and gas to the tank battery. In this case, it's a flowing well. You see that the tubing comes up through the center of the wellhead here. Its pressure, about 1,000 pounds, is measured with this gauge. The production then comes out through this orifice and onto the production battery. This orifice and its insert can be changed to control the rate at which the well produces. The operator will merely close the valves, unlatch this right here, and change the insert size so as to control the flow rate. Larger opening, higher production rate; smaller opening, lower production rate. The pressure between the annulus and the tubing is measured here on this gauge by opening this valve to allow the pressure to be read. There are some other wells producing on this lease using beam pumping. All of the production then from the wells that are going to produce into this tank battery come into it through this header right here. In this black line then we have oil, gas, and water. And that oil, gas, and water, first stop is to this three-phase separator. The oil, gas, and water come in through the black line about the center of the separator, and off of that, the top comes the gas, the bottom the water, and at the mid-phase, the oil. The gas drawn off the top has as its first stop to go to this iron sponge, which collects all H2S in the gas, if there is such H2S in this gas, and it happens to be in some of the gas produced here. The gas passes through the iron sponge downward, H2S is taken out, and the clean gas now travels through this red line and off to be metered. The water is drawn off here in the blue line, and it travels down the blue line to the water tank, where it is picked up from time to time and disposed of properly. The oil comes off this yellow line and goes to the tanks. As the tanks fill, the trucks are called and the oil is metered, checked for quality control, and sold. Let's see how that's done. When oil is to be sold from this production unit, a trucker pulls his truck up to the loading facility, and comes here to the Lease Automatic Custody Transfer Unit, or LAC unit, places his ticket here in the top of the meter, and punches in the number of barrels that he would like to load. He then presses this button, which starts the pump behind me, and pumps the crude from the tanks through this meter, which accurately measures the amount of crude that's being sold, and then into the trucks. Up here we have the BS&W monitor, which accurately monitors the level of BS&W. If the level remains above 1% for more than 30 seconds, this diverter has the crude diverted back into the tanks, and it's not sold. When the quantity of crude that the trucker wants reaches the level that he's after, the pump shuts down. He comes here and removes the ticket, gives a ticket to the operator, disconnects his truck from the sales point, and takes it to the point where he'd like to have it refined or otherwise used. So we see now that it's quite simple to make sure the oil is clean and sold. The gas, clean gas now, passing down through this red line, plus behind me we see red lines coming off the top of the tanks. That's vapor recovery lines. Any vapor coming off the top of the oil is collected, compressed with this compressor behind me, and the clean gas from the separator and the gas coming off the top of the tanks then come through this meter, where with this orifice plate and these pressure taps we're able to record the pressures and the difference in pressures on this 1 week chart. And with this 1 week chart, we're able to measure the volume that's passed through this line during a period of a week. The chart then is changed weekly. The gas at this point in time is at a pressure of about 40 to 50 pounds. The line pressure that we have to deliver to is about 800 pounds, and so we have to compress the gas using a compressor. Let's see how that's done. After the gas leaves the metering station, it comes through a line to a compressor. Now, a compressor is used to increase the pressure of the gas from a low pressure to some higher pressure. In this case, from 50 pounds to the 800 pounds needed to push the gas into the sales pipeline. This compressor is a 230 horsepower compressor. It has two stages. The first stage takes the gas from 50 pounds up to 200 pounds, and the second stage takes it from 200 pounds up to 800 pounds. The gas then leaves the compressor at 800 pounds pressure and travels to its next stop, which is the drip. The purpose of a drip is to remove any entrained liquids that may remain in the gas before it enters the pipeline. The gas enters on the right at the top of a horizontal piece of pipe. It moves along this pipe and the liquids drop out. The gas then comes out of the pipe on the left-hand side, and any liquids drop down into the vertical section of pipe on the left-hand side of the drip. From time to time, the liquids then are collected and disposed of. The next and final stop for the gas before it reaches the pipeline is here, the gas dehydrator, where the water vapor entrained in the gas is taken out of it. The gas comes in here and bubbles up through trays in this column. On the trays is glycol, which removes the water vapor from the gas. The gas then comes out the top and goes on to the point of sale. The glycol, containing now water, comes to the bottom of the column, and through this heater, where water is drawn off, the glycol becomes much more pure again and can be reused in the column. The last stop for the gas before it leaves the production facility and passes to the ownership of the pipeline is here at the pipeline's meter station. The pipeline measures, as we did earlier, the differential pressure and the static pressure in our line across an orifice plate, and that gives them a way of measuring accurately the gas that's passed and sold to them. There are two meters here. The second one records the temperature of the gas as it passes into the sales line. And of course, the volume of gas depends upon pressures and temperature, and so with both of these charts, changed weekly, the pipelines can measure accurately the amount of gas that they are purchasing. As we said, the surface system design for each field will be different. Perhaps the most sophisticated production system designs are to be found offshore.
The wellheads may be underwater or above water. And if above water, the structures used may be the conventional steel structures with driven piles, or gravity structures made of either concrete or steel, or they may be the newly designed guide towers or tension leg platforms. The design constraint for all of these surface systems is that space is limited and production facilities, living quarters, and communications must be included on the platform deck.
You will find additional details on offshore production systems in your manual. Now it's time to take a breather. Please work exercises 1, 2, and 3 in the back of your manual. So far, we have learned what surface and subsurface equipment may be needed for producing a well, but we haven't yet learned how a well's production rate is related to the pressure at which the fluids will be produced. This is the objective of Unit 2.
We begin our discussion by dividing our producing well system into its major components: the producing formation, tubing, choke, surface flow line, and separator. These elements are sufficient to illustrate the concepts involved in describing the pressure flow rate relationships of our production system. All of the components are interrelated. We understand intuitively that fluids cannot be produced on the surface at a higher rate than they flow out of the formation or are lifted up the tubing. We know that fluids flow from points of high pressure to low pressure. What we must do is show graphically how the pressure and flow rates for our system are related. For the moment, we shall consider oil wells and begin at the formation. For illustration purposes, we shall show a plot of pressure, P sub WF, versus flow rate, Q, with pressure on the vertical axis and flow rate on the horizontal. Before a well is opened to production, the pressure at the perforations, P sub WF, is equal to the average pressure in the reservoir, P sub R bar. The flow rate is 0. Because the vertical axis is the well bore pressure, we have a simple point on our graph. Now let's look for a moment at a pressure versus time plot. Without going into the laws of flow, we can state that if we open a well to production at a reasonably constant flow rate, the flowing bottom hole pressure, P sub WF, will soon stabilize. The stabilized pressure drop is called the drawdown. Note in this case that for a stabilized pressure of P sub WF1, the flow rate is Q sub 1. If the flow rate is a higher value, say Q sub 2, the stabilized wellbore flowing pressure will drop to P sub WF2. By testing a well in this manner, it is possible to estimate and plot its bottom hole flowing pressure versus production rate for any given average reservoir pressure. We see such a curve with the two data points for our two flow rates here. This curve is called the inflow performance relationship, or IPR curve. Because the reservoir pressure usually decreases as more fluids are produced, the IPR over the life of a well will shrink toward the origin. This family of curves then shows how a well's potential to produce at any given bottom hole pressure decreases with declining reservoir pressure. Note that if the flowing bottom hole pressure is held constant as the average reservoir pressure drops, a well's production rate will decrease until it no longer flows. Alternatively, if the flow rate is to be held constant, the bottom hole flowing pressure must drop continuously to maintain the flow rate. At some point, the pressure cannot be reduced any further, and the rate must drop.
The inflow performance relationship is a unique description of the performance potential of an oil well. It is the basis for the analysis of a well's behavior. It tells us what flow rate the reservoir will provide at a given pressure.
Just as there is a drop in pressure within the formation during production, there is also a pressure loss within the tubing from the bottom of the well to the surface during vertical flow. This can result in a number of different flow regimes being present during natural flow in a vertical tubing. Because of the complexity of the vertical flow regimes, correlations have been developed which allow us to predict vertical pressure losses in the tubing for a wide variety of vertical flow conditions. These correlations are published as sets of curves, one of which we see here. For any given flow rate, tubing configuration, and production fluid characteristics, the pressure drop in the tubing from the bottom of the hole to the surface may be estimated using these correlations. It is convenient to use the IPR diagram as a basis for the description of pressure losses through our system. We can incorporate the pressure loss in the tubing into this diagram by using the appropriate correlations to estimate the flowing tubing pressure losses at different flow rates. The vertical axis is now pressure rather than P sub WF, and the new curve represents the tubing head pressure, that is, the pressure at the wellhead at the different flow rates. Once the well fluids reach the surface, they must flow through the choke, gathering line, and surface facilities before reaching the point of sale. Chokes are normally selected to maintain a critical flow velocity. When critical flow occurs, the upstream pressure is about twice the downstream pressure. This means that the pressure is reduced by a half as it flows through the choke. The choke effect can be added to our pressure production rate curves by plotting a curve equal to 1/2 the flowing tubing pressure at each flow rate. This new curve represents the pressure just downstream of the choke. The next surface component is the flow line. It causes additional pressure losses in the system, and so we must add a fourth curve to our figure. The value of these losses is estimated by using the appropriate horizontal flow correlations. For our specified flow system, we now know the maximum pressure available at the separator for any given flow rate. We can take our diagram one final step by adding a line which depicts the minimum pressure required to operate the separator. The flow rate where the downstream flow line pressure curve intersects the separator pressure line is the maximum practical production rate for the well, and for which the choke and other equipment must be sized. We may summarize the system pressure losses that occur at this production rate. Beginning with the average reservoir pressure, we observe the pressure losses in the formation, up the tubing, across the choke, through the surface lines, and separator. In a sense, the reservoir pressure drives the whole system and is used up along the way. If we wish to increase the flow rate, changes must be made to the flow system that reduce some or all of these pressure losses. Keep in mind that the basis of this diagram is the IPR curve, and that it will change with time.
Using this type of analysis, the engineer will select a maximum production rate for each oil well in the field, and then design the necessary subsurface and surface equipment to handle all of the wells producing into a single separator. Developing a performance relationship for a gas well is different from that of an oil well. For details concerning gas well testing, please see your manual.
If the bottom hole pressure of a well becomes so low that the well will no longer produce at a desired flow rate, or perhaps at any flow rate, some sort of artificial energy supply is needed to help lift the fluids out of the well bore. Energy can be supplied indirectly to our well by injecting water or gas into the reservoir to maintain reservoir pressure, or directly through a variety of artificial lift methods which are applied at the producing well itself. There are many artificial lift methods. However, all are variations or combinations of three basic processes. The lightening of the fluid column by gas injection, usually referred to as gas lift. The subsurface pumping of liquids using beam pumps, hydraulic pumps, and electric submersible centrifugal pumps. And the piston-like displacement of liquid slugs, commonly referred to as plunger lift. The first two of these three categories are in greater use than the last, so we shall restrict our discussion to them. Let's begin with gas lift. Gas lift provides artificial lifting energy for our well by the injection of gas into or beneath the fluid column. The gas decreases the fluid density of the column and lowers the bottom hole pressure, allowing the formation pressure to move more fluid into the well bore. Injected gas bubbles also expand as they rise in the tubing above their injection point, pushing oil ahead of them up the tubing. Gas lift may be either continuous or intermittent flow. Continuous flow gas lift relies on the constant injection of gas lift gas into the production stream through a downhole valve. Intermittent or intermitting gas lift allows for the buildup of a liquid column of produced fluids at the bottom of the well bore. At the appropriate time, a finite volume of gas is injected below the liquid and propels it as a slug to the surface. Let's go to the Gulf Coast and see an example of a gas lift installation.
We have a source of high pressure gas that comes from the compressor station, comes in the line right there. You have a valve, actuated valve with a controller on it. This one happens to be a pressure actuated controller. It allows how often the gas will come in. It just operates the valve, open or close. You have a low and a high pressure setting. When it reaches the low pressure setting, it needs to get more gas. You'll sense the gas, it'll open the valve. You'll get a gas, you'll get an increase in casing pressure until you reach your high level. The high level will shut it off, the valve will close. You've injected gas in the annulus, and you'll see a rise in the tubing pressure as you start to produce fluid out the flow line in the back. And this is what we call a DAP unit, it's pressure actuated, and then there's a timing unit. You just set off for 20 minutes, on for 30 seconds or something like that. And it actuates just on time. We're keep track of tubing and casing pressure, pretty regular. And then we also we monitor how much gas it makes, how much water it makes, how much oil it makes.
Subsurface pumping can be achieved by various methods. The most common is sucker rod pumping, where the pumping motion is transmitted from the surface to the pump by means of a string of rods placed within the tubing. The subsurface pump is essentially a plunger and valve arrangement within a tube or barrel. When the close-fitting plunger is lifted within the barrel, it creates a low-pressure region below the plunger, which is filled by fluid from the formation, and simultaneously the plunger and rods lift fluid up the tubing.
The majority of subsurface pumps that do not use rods fall into two categories: hydraulic and electrical submersible. Hydraulic pumps rely on the use of a high-pressure power fluid which is pumped from the surface to operate a downhole engine and pump, which in turn pumps both power fluid and crude oil to the surface. Electrical submersible pumps are simply downhole electric pumps supplied with power by way of a cable. Artificial lift methods allow us to maintain production from a well when the reservoir energy is not sufficient to lift the fluid to the surface. As we have seen, there is a wide variety of artificial lift methods available to the production engineer. The particular method chosen for a given well will depend on factors such as the pressure, fluid types, space limitations, power requirements, well depth, and operation experience. While gas lift is the major method of artificial lift employed offshore, rod pumping is the most widely used artificial lift method onshore, especially in the United States. We should point out that sometimes the newly completed well requires artificial lift from its first day of production. In other cases, the engineer knows that it will be needed later in its life. For these reasons, the drilling and completion programs are often designed to accommodate the artificial lift equipment that will be necessary even when the well first flows on its own. For now, let's summarize what we have learned. We have seen what subsurface and surface equipment is needed to allow us to produce, process, and sell our oil and dispose of our produced water. We have seen how the pressure-production rate relationship for a well is determined and how it changes with time. And finally, we have learned about the various artificial lift methods and why they are needed. In your manual, beginning on page 102, we have listed a number of interesting production systems from various fields around the world. Please take a moment to review them and at the same time work exercises 4 and 5.